Okay, thank you. So first, thank to the organizer for the invitation. I hope the talk will raise up many questions after. So I will start. So by so it's a first it's a joint work with Ajmal Odali, which has done this work during his PhD. And with my colleagues, Clara Goethals and Luc Duchâteau of the Faculty of Veterinary Medicine in Ghent University. So the motivation of the work comes from some malaria dataset, which Luc and Clara have already analyzed. And so I will start with a few information about malaria diseases. So malaria was eliminated in the 50s in America and in the 70s in Europe, but today it is still present in some part of the world. So we have more than 200 million of malaria cases worldwide in 2017. We have more than 400,000 deaths, and most of the deaths are children under the age of 5 years. So I think there is something in the chat.
Mais Estelle, en fait, on voit toujours la slide de titre. Je ne sais pas si c'est normal.
Not here, so maybe I come back to this.
Ouais. Là, on voit la suite.
Okay, so maybe I stay.
Yeah, that's fine.
C'est bon la taille comme ça quand même?
Ouais, non, c'est très bien.
Ouais, okay. Okay, so and also we have no significant progress towards the decrease of the number of malaria cases between the two last years. And so we can also have a look on this map from the World Health Organization. So it's for the year 2017, and you can see that countries who are colored in white have no malaria. In yellow, so China here have 0 cases in 2017, and quite the same for the countries in blue. And in, I say red or orange, dark orange, the countries will have 1 or more cases in 2017. So most of the countries with malaria today are in the South Hemispheres. And I will not try to explain you how malaria, to better understand how malaria propagates. So we have a look of on the mechanism. So it starts by a mosquito, which is first infected here. Then mosquito propagates the diseases on the first infected human. Then some process in the human, and a second mosquito can be infected when he comes in contact with the human, and then he can infect a second human. And after, mosquito will be dead. So what we can see here is that mosquitoes indeed play a key role in malaria propagation for the transmission. And besides this, we can observe that several dams were constructed in Africa, in particular, to retain water for the population need, which is quite a positive purpose. But a drawback of these new dams is that it creates lakes which are indeed good places for the development of population of mosquitoes. So the objective, we have indeed a data set, a rich data set, which is collected in Ethiopia. So here you have Ethiopia, which is located in Africa. And we focus on around Jima here. And so in the Jima zone, we have in particular one big dam here, which is Gilgel-Gibe Dam. And here we have a focus around the dam. So we can see that around the dam, there are 16 villages, which are represented by the the green points. Okay, so you have 16 green points here all around the dam. And the individual households are represented by black points. Okay, and so the idea is that the proximity of the villages or of the household to the dam can have some effects on the transmission rate of malaria. And also, because of the transmission mechanism, the proximity between individuals in the village, in the different village, can also have some impacts of the propagation. And so, indeed, the objective is to propose a model which take into account the distance to dam, possibly as a covariate, but also the distance between the individual. And so to quantify the effect of the dam on the malaria propagation. And the previous analysis have been done with model which did not propose to take both together, or indeed they try to take both together, but they consider indeed the proximity not between individual but between villages. So it was not satisfying because, as you can see, there are some villages here, for example, which are quite near one, both are quite near together. And there are some households who you don't know if the household, you know from an administrative point of view, but it's not the important things here, but you don't know, indeed the proximity of the villages is not what we want to take into account in the model. So I will present briefly the context of survival analysis with the quantity involved, also the general frailty model and the model we propose with spatially correlated frailty terms. We shortly present the estimation procedure, which will be a stochastic EM algorithm, as Patrick said, and some simulation study first, and then the analysis of the real data set from the Gilgel-Gibe Dam. So for the context of survival analysis, I will consider an event of interest in a population of individual. I will denote by TY this event, this time to event, sorry. And then as example, you can consider time to infection, if, for example, in the malaria application. You can also consider time to death. In some application at INRAE, we consider time to flowering date for some plants. You have also application in economy. We can consider time till recovering a job after an unemployment period and so on. So the quantity involved in this type of analysis is the survival function. So it's just the probability that the event occur after time t. You can also consider the hazard, which is indeed the probability that the event occurs at just after t, knowing that it has not occurred before T. Okay, and you have a link between the hazard and the survival function by this integrate formula. And I will also quickly introduce the Cox model, which is the most common model, I think, which is used to link the hazard to covariates. So here you have an unknown baseline function, which depends on the time. And you have covariates of individual I and parameter vector beta, which is of interest and unknown. And this parameter beta will quantify the effect of the covariates xi on the hazard of the individual I. So there is some inherent hypothesis to this Cox model, which is called the proportional hazard assumption. So indeed, I recall that I have this expression of the survival function in function of the hazard. And in Cox model, we have the hazard, which is equal to this formula. So this leads to this type of equation. Okay, and so you can see that here you have a quantity which depends on T, and the dependence on T is present here only, and not in the covariate part here. So if you do some plots, for example, here I have two groups in my population, group 1 and group 2, and two covariates value different in these groups, so x1 and x2. If I do the plot for the two groups, you can see that you just have a shift between the two curves, and this is inherent to the Cox model, and it can happen that your data didn't check this assumption. So in particular, if you have heterogeneous data, you may switch to another model, or so there is a few ways to consider this. So you can, for example, take covariates that depend on time. So time is not only here, but only in covariates here. Or another way is to consider frailty models. So the idea is to model heterogeneity in the population with random effects. So for example, you have a concrete situation where you can see some structure in the population, sorry. So for example, if you consider clinical study in several centers, you will have some different effects depending on the center on which you are regarding the study. In agronomy, you have also, for example, crop on several parcels and in several environmental conditions, and this will contribute to have heterogeneity in the data set. So the objective is to model this heterogeneity. So we denote by I the indices of the group, the subpopulation in our population. So for example, here a group can be a center in the clinical study, and we will denote by J the indices of the individual in the group I. Okay, I'll denote the group and J the individual. And now we will model the hazard through this way. Okay, so you have a covariate Xij, and you add here a random effect By, which is shared by all individuals in the group I. And so this random effect represents the heterogeneity between the group. Usually, these random effects are supposed to be identically distributed and independent between the group. And so, for example, the malaria dataset has been analyzed with a random effect at the village level. Okay, so if you think to the household were clustered in 16 villages, and in each villages you have several households, and so you have a structure in your population. And this has been done to analyze, this model has been used, to analyze this data set. But it was not satisfying, because this random effect at the village level does not take information about the proximity between individuals. So we propose this spatially correlated univariate frailty model. So the idea is to introduce spatial correlation in the frailty term, but the frailty term is at the subject level. So it means that each individual will have its own frailty terms. So we model the hazard as follow. We forgot the structure in the population, so there is no more the indices J, okay? I is now the indices of the individual, and we have a frailty term here for each individual. And now we will choose the distribution of this frailty vector. So B is the vector of all the frailty terms. Here I have big N individual, and we choose a Gaussian centered distribution. And here we put a covariance matrix with some structure depending on some parameter rho. Okay, sigma square is a scaling factor. And now how to choose this correlation matrix. So there were different existing correlation structure in the literature. And so we consider the two most common, which are indeed an exponential form and a polynomial form. And D, big D here represents the matrices containing the distance between subject I and subject I prime as the component I prime. And now we also consider a parametric baseline for the baseline hazard function lambda 0. So the usual things are variable, compared, or constant, or piecewise constant parametric form. And in general, we denote by alpha this parameter. So the whole model parameters are theta, containing so alpha from the baseline hazard, beta, which is vector, the regression vector of the covariates, and sigma square and rho, which are the parameter of the covariance structure. And now I will just quickly explain the observation process in survival analysis, which often is censored. So what is censoring? Indeed, if you consider different subjects here and the time on the x-axis, so at the beginning of the study, you follow 4 individuals and you observe if the individual, if each individual, if the event of interest occurs for each individual. So the blue point represents the event, okay, and is white or color inside, depending on the event is observed or unobserved. So here you can see this both individual are observed because the event occurs before the end of the study, which is represented here. And for the 2 other people, we have censoring for different reasons. So here, for example, we didn't observe the event which occurs after. So it's not specified here, but maybe this individual go out of the study for personal reason, I don't know, okay. And here in the second situation, the event occurs, but after the end of the study. And so we have to model this censoring effect. We have Ty and Cy, the censoring time. These both times are usually not observed, and we only observed Yi and delta I, which is the censored observation, and delta I is the censored indicator. And so to do inference on the parameter theta, the observation we have are these both observations. Okay. So now for estimation, we will do marginal maximum likelihood estimation for the parameter theta. So marginal because we have latent variable, which are indeed the frailty terms. So we first write the complete likelihood, which has got this expression. This comes from the frailty model. Okay, so you express the likelihood given the frailty By. And here you have the distribution of the frailty term, which is Gaussian with this covariance matrix. And now from this complete likelihood, you can deduce the marginal likelihood by integrating out the frailty terms. And so the objective is to maximize this marginal likelihood. And so you can define theta hat. Okay. So we target the value of theta hat. Since you do not have a closed form for this marginal likelihood, you have usually to use some numerical algorithm. And so in frailty models, there are many propositions. So you have a few propositions based on approximated likelihood criteria. I will not go into the details because of time. You have also Bayesian approach and some exact likelihood based on the EM algorithm and stochastic version, which are proposed. So we have chosen some stochastic EM algorithm, and I will first present the EM algorithm. So it allows to deal with estimation in latent variable model in general. And you at iteration K, you have two steps. First step, you have to compute an expectation, which is here. So it's a conditional expectation, conditional to the data and to the current value of the parameter. And you use this conditional expectation to update the parameter during the end step, as follows this equation. Okay. And so you have good properties, you converge toward the critical point, and there are drawbacks, but the main drawback, I think, is what can you do if the E step is intractable? So you can go toward, move towards some stochastic version, and we choose the stochastic approximation EM. And we had to take the version which couples this algorithm with Monte-Carlo Markov Chain method due to the complexity of our model. So just briefly, at iteration K, indeed, you have 3 steps now. So the maximization step will remain unchanged, but it's not the same quantity Q that you use to maximize and update the parameter. The E step is split into 2 steps. The first step where you simulate the latent variable, sorry. So you simulate it through a transition kernel P theta, which generates an ergodic Markov chain. And the objective is that this Markov chain has a stationary distribution, the posterior distribution. So it's a posterior distribution of B knowing the data. And after you compute the stochastic approximation of the log likelihood, log complete likelihood, using the simulated value you just perform here. So you plug it here and you perform this stochastic approximation. Gamma k here is a step size, positive step size satisfying this condition. And you can prove, under given assumptions, that this algorithm, which is stochastic, so it's an almost sure convergence toward the critical point of the marginal likelihood. Just some quick heuristic about stochastic approximation. So here you have the dynamic of the stochastic approximation. I can rewrite this. So like this increasing weight, okay? And so imagine gamma k is quite little, okay? And you have here, I put artificially this quantity, which is the quantity of interest in the EM algorithm, the Q quantity of the E step. So I put it here and minus here. And so you have indeed two terms. So the second terms, we can see that if this quantity here is simulated under the posterior distribution, you have here a centered term, which I denote by EK here. And under some assumption, I can control this perturbation. And then I see that if QK converge here towards 0, so the increasing rate is converged to 0. Here you see that QK indeed converge towards the quantity of hysteresis. So QK is in the stochastic version a sequential approximation of the quantity which is involved with the E step in the EM algorithm. So we use this algorithm. We have performed first a simulation study. So the objective was to mimic the malaria dataset. We consider a model called model M1. So here you have the hazard, which is modeled like this. And we take first distribution with this covariance matrix, so the exponential form. We consider 300 subjects, which is less than in the real data set, but we start with only a few individuals. And for the matrix D, we choose value of the real malaria data sets. And for the the baseline function, we take piecewise constants because indeed we want to model the seasoning effect. So we have data on 2 years, and each year you have 3 seasoning depending on the rain, which are more or less important. And so we suspect indeed that this rainy season have some effects, and we choose this way to model the baseline. We sample the covariates from a Bernoulli distribution. Here you take the value for parameter beta, sigma square, and rho. We also consider 3 different censoring settings to investigate the effect of censoring on the estimation quality. Since we have to face for the simulation step to the high dimensional vector, frailty vector, we consider a random scan metropolis algorithm, so GIPS, and I present here first the result when we simulate 100 repetitions of the data generated under model M1, and we perform the simulation in the model M1. Okay, so we have no bias coming from the modelization. So what I only put some parameters, not all, because the results are of the same order. So here you have 1 parameter of the baseline, 1 parameter, regression parameter for the covariates, and the 2 parameters for the frailty distribution. here you have the true values and what you can see and the estimate obtained and also the empirical standard error in parentheses. And so what we can see is that the estimate is quite near to the true value in each case, also with 60% of censoring, which is quite important. You see also that the empirical standard error increase with the censoring, which is quite expected. Okay, but results were satisfying with only 300 subjects. In the real data set, we have more than 2,000 children. Now we also investigate the robustness to misspecification of the correlation structure. So to evaluate these effects, we introduce a second model called M2. It's the same model. We only change the covariance matrix of the frailty vector. Here we consider the polynomial form. And so we play the following game. We estimated the parameters in model M2 with data simulated under model M1. Okay, so under the wrong correlation structure. And so the results are presented in the table. So it's the same table as before, but with the estimation considered here. And so you can see that the parameter from the baseline is, there is a little bias from the estimation regarding the true values. The regression coefficient is quite good estimated in all the settings. And there is also a little bias in the estimation of the correlation structure, which is indeed modified in model M2. So it's not, I don't know what we can expect, but we play the game to see how it, what is good is that the regression coefficient is good, is well estimated, also with the wrong correlation structure. So now we compare also the model with other model without spatial correlation structure to see if the spatial correlation structure brings something positive in the estimation task. So we consider first the proportional hazard model with a piecewise constant baseline and no frailty term. Okay, so it's like the Cox model, but you specify a parametric form for the baseline. And the second model we consider is a univariate frailty model. So you have a frailty for each individual, but indeed you take a frailty independent, identically distributed without correlation structure. Okay, and so we play the following game. So we simulated data under model M1. And we estimate data, the parameter in model M3 and M4. And so what we can see, so here you have the proportional hazard model. So in part, I put all the parameters in here. Okay, you can see that the regression coefficient of the covariate are biased. Okay, so you can, it means that the conclusion that you can have with the interpretation you do from this estimation can be wrong, okay? Because you will see how the covariate 1 and 2 affect the hazard, and the coefficients are not good. The estimation of this coefficient are not good. Okay, and here, if you consider the univariate frailty model, it's also biased, but less than here. Okay, so the frailty term do its job, but you don't take into account the correlation between individuals. And now I will move to the, okay, yeah, just have a look to time, it's okay. I need 5 minutes, I think. to the analysis of the data set from the Gilgal-Gibber malaria infection time. So we have more than 2,000 children, 16 different villages, and we consider 4 covariates. So first covariate is the distance to the dam, distance from the household to the dam, okay? We also take into account the sex and the structure of the roof of the household, because this structure can indeed allow the mosquito to go more or less inside the house, okay, depending on how strong it is and so on. And the age of the children, so we have two value possible, two modality, age between 3 and 7 and age more than 7. So the result we obtained, so with the spatially correlated frailty model, indeed, we choose first the correlation structure between polynomial and exponential. We select the polynomial structure just by comparing ISA criteria. We also test the presence of correlation. So we test the null hypothesis rho equal to infinity using a likelihood ratio test. So you have to pay a little bit attention here, because you have a value which is on the boundary of the parameter set. So the limiting distribution is a mixture between a Dirac and a chi-square 1. So just to pay attention here. We test the effect in particular. So we have no significant effect for the covariance distance to dam, which was not expected, but also obtained with other model. And we have a significant effect for children older than 7 years. In particular, we obtain a higher malaria risk of 42%. Then we also try to analyze this data with other model. So, for example, we obtain with the shared frailty model, which is what we call the shared frailty model, is 1 frailty per village. Okay, I have presented this model before. So in this model, we also obtain here a significant effect for children older than 7 years. The malaria risk was about 38%, so it's quite the same. But we obtain other conclusion. Indeed, in this model, you obtain when you increase the distance to dam, you obtain a decrease of the incidence, which is quite what you expect. But in our model, we obtain the opposite. So meaning that when you increase the distance to dam, you also increase the incidence. Indeed, it's not, we don't try. There was some criticism about the shared frailty model, in particular because of what we call confounding effect between the distance to dam and between the frailty which is at the village level, because you see that the frailty at village level include also the distance to dam, because the households are so near in one village that they indeed have all the same distance to the dam in some, mostly speaking, they have the same distance to dam. And so this one of the drawback pointed out in a previous paper about this analysis. And so our model does not have this drawback. So just to picture quickly, We also plot the hazard weight estimates for the baseline. So depending on the time here, about 2 years. And we indicate here the average daily rainfall for the different time period. We don't have done much studies, but what you see is that the hazard is low when the rain is low, and the hazard globally is higher when the rain is globally higher. Okay. And then we also have a look at the correlation as a function of the distance between the individuals. So we plot the value of the correlation structure of the frailty as a function of the distance. So here on the x-axis, you have the distance and the correlation value here. So it's just, we call a polynomial function here. And what is represented in red is this 2 kilometers, which is the theoretical maximum distance covered by a mosquito. So you expect that the correlation function is not so important after the 2 kilometers because the mosquito have to go from one individual to another, okay, to propagate the malaria. And so I have just a little conclusion and perspective. So we propose the spatially correlated univariate frailty model. We propose also a convergence estimation algorithm. I don't mention it, but we have some theoretical proof of convergence for the stochastic algorithm. And we perform the analysis of the malaria data with this model, in particular taking into account the distance to dam and the distance between individuals without confounding effect. So the perspectives, we can take into account more complex correlation structure in some example. It would also be interesting to consider partial likelihood estimation. So this is done in the Cox model. You consider the partial likelihood where you profile indeed the likelihood on the baseline lambda 0. And so your estimation did not depend on the modelization you choose for the baseline. So this could be of interest in such model. And indeed, we know how to perform it, but we have not done it for the moment. And we can also consider other diseases with different transmission and so on to model different correlation structure. And so I give just a few bibliography references. Okay, and I will thank you for your attention. If you have questions, please.
Thank you, Estelle. So, any questions for Estelle? Maybe a very basic one from me. I'm not very familiar with these SAEM estimation algorithms, but how do you get the confidence intervals? I mean, the variance around your estimates from the
here we perform empirical ones. So we perform 100 estimation.
Right.
And we just got the empirical, but
okay.
you can also consider standard error, which are model-based, and okay. You have to estimate the Fisher information matrix, which can also be done. I just not present these results.
Using also a stochastic algorithm.
I prefer using some Monte-Carlo approximation because the stochastic approximation you can do it with stochastic approximation, but indeed we work about a new estimator for this Fisher information matrix in latent variable with mode de Lattre, and because the previous one, which was proposed by stochastic approximation, is quite unstable. Unstable meaning you need to perform more iteration than for the estimation of the
right.
parameter.
Yeah, I see. Okay, so maybe first Charlene, and then the question in chat.
Yeah, it's certainly a naive question, but you listed several EM models, and how do you choose the one you use? So the stochastic EM models in your case. So
you mean procedure, not model?
yeah. The algorithm. Sorry, the algorithm.
Okay. So indeed, sorry, I just go here. I did not get into the details in this algorithm, but when you consider procedure using approximated likelihood criteria, indeed, when you do an approximation, you lose indeed something, okay? And in most of these cases, so for example, when you do here a penalized likelihood, you involve spleens and something like this, you cannot control the error coming from your approximation. And so usually people show many examples and the methodology work on this example, but you have no theoretical properties for the procedure. And in the exact, the methodology based on exact likelihood, so indeed you do no approximation of the target criteria, but you approximate numerically due intensive simulation, several quantity in the EM algorithm. So indeed here in the EM algorithm, you do no approximation, but you cannot use this EM algorithm in complex setting. You can perform EM if you choose a gamma frailty distribution. And in other setting, it's not possible. So you have to go towards stochastic algorithm. So here, if you consider the Monte-Carlo EM approximation, indeed you approximate the Q function in the E step by some Monte-Carlo sum. And here I write the different references. So this algorithm was indeed proposed here by this author in 90 for general model. It was developed in the frailty context by Ripati and colleagues in 2002. And we get a theoretical analysis of the algorithm for general model by Faure and Moulin in 2003. So here you have the whole package. Everything is good, but you have a long computation time. And since we have a big frailty vector, so 2000 in the real data set, it will be too long here, okay? And here you have another EM approximation, which is based on the Laplace approximation, the common Laplace approximation for integration. And here you have no convergence property. So if your Laplace approximation performs good in your setting, it's okay, but you have no, there is no reason it will perform good in each setting. And so we consider the stochastic approximation EM because it's indeed the same spirit as this one. You have also the theoretical properties of convergence for the algorithm, and it's quite much more faster for computation time.
Okay, thank you very much.
Is it okay, Charlene? Yeah.
Yeah. It's thank you.
Okay.
I think Christophe had a question in the chat.
Okay. Attends, I have to have a look in the chat. What is the distribution of the distance between the lake and the different villages?
I mean, the reason why I'm asking the question is since you don't find any effect of a distance to lake, and since you mentioned that if you are farther than 2 kilometers, you consider that the mosquito cannot travel farther than that.
Yes.
Is it that the villages are too far?
Yes, I think I have not the the scale in mind. Sorry, can I move this? Do you see the black?
Yeah, I see. Yeah.
Okay, because I don't see the scale, it's just behind. Okay. Here
so
have...
at the bottom you have it.
Yes.
Yeah.
Maybe I can have a look on the paper. I don't know, but it's more than 2 kilometers.
Yeah,
I
so
think
there's a significant number of villages that are too far away, in fact.
Yes, it's not, I don't see. Okay, but I think you are right, and this is probably the reason for that we don't find a significant effect from the distance to dam.
And it's known what's the preference for the anothel to lay eggs. Because I remember from a long time ago reading the book of Hackett, who was the guy who took care of eradicating malaria from the US and then traveled to Italy to do the same thing in the 30s. And he said that at the beginning, they failed in Italy because they thought that the anothels in Italy laid eggs along streams, like in the US.
Yes.
While they in Europe, they lay eggs on stagnant water. So
yes.
it took them a long time to realize that the different species had different habits. And
yes, and I think in this data set, so in this region of Ethiopia, we have two kind of plasmodium. I don't remember, falciparum and something other. I don't know their preference for the legs. And indeed, I was wondering, because you see on the maps that some villages are very near from the dam, and some other here are very far.
Yeah.
And maybe if we analyze only a subset of the data, taking into account villages that are near from the dam, maybe we will observe an effect from the covariate distance to dam. But I don't know. And also, I don't know if there is, because I think the dam is quite big. So maybe mosquitoes are not present of the same way in all regions of the dam. I know that there was a study where you have a joint model taking into account some mosquito density also.
Okay, thanks.
I was wondering something actually that's a bit related to that. If you, for instance, if you take the villages that are quite far from the dam,
yes,
and you could maybe assume that if malaria were to propagate starting from the dam, then it would have to go through another village first.
Yes.
And so wouldn't there be a sort of temporal structure in your data, meaning that the village on the bottom would be infected last, and so the curves would be there would be a time lag somehow in the data. I don't know if you can see something like that. I haven't seen the raw data.
Yes, I think we didn't look at this. But you think to first transmission, second transmission, and so on.
Something like that. Yeah, but of course, it strongly depends on the way malaria. And if there's another reservoir of malaria, which might make it endemic, and yeah.
Yes, I don't know if such dynamics exist or not. We have data on 2 years, so I think there is some continuum on the 3 season, but indeed we only have the time to infection and the covariates, okay, but maybe to have a look at what you suggest, we have to consider time to infection in function of on the distance.
Yeah,
or something. Yes. Okay.
It's a bit weird, maybe, and you also have maybe this temporal structure that you were. I mean, you were talking about it in terms of rainfall, but I'm assuming it has.
Yeah, I think to something else. Indeed, I think Luc have tried to model also a different way of transmission, which is from a mosquito or it's indeed only with mosquito, but between individual who are very near one to the other, or between individuals who are more distant. And I don't know. I understand what you want to suggest.